All right, so the wavelength used here. So I'm going to try to find what my wavelength is. That's a different color. Let's change that back to black. So that's my goal. So we know two things about this here. We know that the slit distance is 2 times 10 to the negative 5 meters apart. So that's good. The distance from the first order maximum, which remember maximums are the antinodes of the bright spots. So the first order means number 1, and the maximum, the distance that would be x. So 3 times 10 to the negative 2. What else do we know? Well, it tells us the screen length here is 165 centimeters, so 1.65 meters. I'm just going to change that to that. So what do we need to do? So I want to find theta is equal to d sine, or sorry, lambda, sorry, is equal to d sine theta over n. Now to use this, because we have the d and we have the n, which is 1, to use this I need to find theta. So I'm going to use the tan theta here, making sure my calculator is in the right mode, to find out what the angle is. So you would always do this step anyway to make sure that the angle is an appropriate size, because you could use the bottom formula if the angle is small enough, but I don't know if it is small enough yet. So I'm going to type this in my calculator. And I'm going to go tan inverse to find my angle. Oh, sorry, x over L, my bad. I had the x in the right spot, but my L is 1.65. Now I'm going to go tan inverse of that, so that makes more sense. Tan inverse. Get 1.04 degrees when we do this one, 1.0416 degrees. Okay, so if I know the angle, that's a 1 degree, so technically I could use this bottom equation, but since I know the angle, why not just use the top equation? So let's put my d value in there, so 2 times 10 to the negative 5 sine this angle that we just found, divided by n, which is 1. So technically, I don't have to divide by anything. So I go sine this angle. If you look at that, I know it's going to be backwards on yours, but you look at the two numbers. The top number is my tan ratio, and the bottom one's my sine ratio. They are pretty close to each other, so that approximation does kind of work for small angles. So sine and tan could be the same, just for small angles, though. Times my d value here, and I get a wavelength of 3.64, let's go 3 sig digs, yeah, times 10 to the negative 7 meters. I'm just going to change this to nanometers because that's just a nicer way to communicate this. So 364 nanometers. Cool. Pretty good. That's all we need to find out and calculate the wavelength. Yeah, that's all I used. So here we know the wavelength of this light. So this is lambda here, so 530 nanometers. I'm going to just change that to meters. Calculate the distance between the slits. If the angle between the central maximum and the second order minimum is 16 degrees. Okay, so we're trying to find D here. They're telling us the angle is 16 degrees, and they're also telling us the end value is to a minimum. So this is a dark line, right, or a dark spot. So my end values are going to be some kind of half number. It's a second order, so it's the second one over. So I'm just going to kind of just put a little sketch over here. So here's my middle line, 0. Here's my next bright spot, and there's my next bright spot after that. All right, so this is my slits are down here, my screen is over here, these are the bright spots. So this is going to be my first dark spot, and this is going to be my second dark spot. So my second dark spot's at 1.5. Okay. yeah, so we have enough information just to use this formula as is. So I don't have to find any angles or anything. So I'm going to rearrange this for d. So times the n up to the lambda side and divide the sine theta down. And we just put our numbers in. Now, if we leave the 530 in nanometers, you're going to find your answer in nanometers. So I changed it so we get our answers in meters. And the angle is quite big here. That's fine. So we get a d value of 2.8, 3 degrees again, 2.88 times 10 to the negative 6 meters. So 2.88 micrometers. I'm just going to leave that in scientific notation. So the next few questions here, I believe, yeah, the next few questions, it's all about diffraction gratings. So say this first one here, light is shone on a diffraction grating that is scored with 5,000 lines per meter. So that is going to help us find the d value, this 5,000 lines per meter. So I'm going to go 1 over 5,000. It's in meters already, so I'm just going to leave that in meters when I get my answer. So this is going to be 2 times 10 to the negative 4 meters. So whatever this was is whatever this is going to be as well. So if it's in per centimeter, you get centimeters. I recommend changing it after you find the d value. Just makes it a little bit easier to change between the two. Most of my formulas do not use frequency though. The 6 times 10 to the negative, or 14, sorry, hertz. So I'm going to use the universal wave formula, f lambda, to help me figure out what the wavelength is. So it's going to be c divided by my frequency. So remember, c is the speed of light, divided by my frequency. And we have 500 nanometers. So this is actually going to be 5 times 10 to the negative 7 meters. Okay, keep it in meters because everything else is in meters. They tell us the screen is a meter away, so that's going to be my L distance here. What are we trying to find now? Calculate the distance from the fourth order to the fourth order maximum. So this is a maximum, so this is a bright spot again. So that means my n is 4, just 4. And we're looking for x. We're looking for that distance. So this is all the stuff that we have in our givens. We're looking for x, but the thing to find the x, we have to either make an assumption that this angle is really, really small, or find the angle to just to verify is the angle really, really small. So I can use the other formula. So I might as well just find the angle. So I have enough information here to solve for sine theta, and then I can take the sine inverse of all of that. Okay, so that's what I'm going to do first. I'm going to just type in my numbers that we know. And then I'm going to go sine inverse that number. It's a pretty small angle actually, so this ends up being 0.5729 degrees-ish. There's a lot more decimals there. But now, because I have the angle, I might as well just use the XL tan formula instead to find out what x is. So I'm going to times the L up. And then I'm going to go tan theta. It's going to be times 1, so I really just have to go tan my angle times 1. So this ends up being 0.01, how many sig digs? 3 sig digs, 0, 0. Yeah, 1, 2, so 1.00 centimeters. If you want to put in different units, that's fine too. Okay. So here, this one here, they want to find the number of lines per meter. So to do that, I'm going to have to find out d, so I can find out what 1 over d is specifically. That's the goal, is to find out this part here, the 1 over d. Second order minimum. So I know the second order minimum number from previous is 1.5. The angle is 15 degrees. The light we're using is 5.25 times 10 to the negative 7 meters. And it says here calculate the lines per meter, and then here it says calculate lines per centimeter as well. Okay, I'll just find both. I'm looking at this right now. I have enough information just to solve for D. So it's D. I should probably write out the formula first. Let's write out the formula. Let's get rid of this piece. Okay, it's going to be D sine theta over N. And then D is going to be N lambda over sine theta. And I'm just going to plug these numbers in. So 1.5 times this 525 nanometers divided by sine 15. Okay, so when I do that, I get a D value of 3.04 times 10 to the negative 6 meters. Because this is in meters, if I go 1 over this D, 1 over this number, what I'm going to get is how many lines per meter. Okay, so I get about 328,000 lines per meter. We change that into proper signatures. I'm going to leave that the way it is. But what else I'm going to do is I'm going to change this number to centimeters first. So I'm going to go back to my previous number and change that into centimeters. So if I change that into centimeters, I'm going to get 3.04 times 10 to the negative 4 centimeters. And then I'm going to go 1 over the D on this one, 1 over my D. And I should only get 3,287 lines per centimeter. So it's a much nicer number there. Okay. There we go. Pretty good. White light's directed at a diffraction grating that is ruled with 50,000 lines per meter. How wide is the first order spectrum of this? Okay, now this is where it gets a little bit, they just want to know what the distance between the red and the violet. So remember when you put white light through a diffraction gradient, it's going to diffract outwards or change into a rainbow because the red light will interfere at a further distance because its wavelength is longer. So the two wavelengths I'm going to deal with here, I'm just going to mix some numbers up here. So 800 nanometers, that's my red light. And let's just say, to simplify this down, let's just say 400 nanometers, and like 380 or something for my violet, so the end of that one. My D is going to be 1 over this 50,000 number. It's going to end up being meters, so 1 over 50,000 is 2 times 10 to the negative 5. 2 times 10 to the negative 5 meters. Okay. How wide is the first spectrum? So I'm going to do N is equal to 1 here. My L is 1.20 meters. Looking good. We need to find the X for the red and the X for the violet. So how far over is the red from the center and how far over is the violet? So there's going to be a difference between those two because the wavelengths are different. And I know that because I can use that other formula, the one we don't like, XD over NL. If I rearrange this for X, that's what we're trying to find anyway. I could see that if my wavelength were to go up, so would my X, right? If other things that we can glean from this is if my distance goes down, so does my X. Or sorry, not so does my X. So my X goes up because they're inversely proportional to each other. If the distance to the screen goes up, this also goes up, right? So that's all that formula really could be used for. That's all I want to use it for, is to kind of see how if I manipulate a variable, how does that responding, the distance between the central node and this bright spot is. How does it change? But we're not going to use that one, so we're going to use this other one, d sine theta over n, and we're going to use the tan theta, XL formula. So L times tan theta. So I'm going to use that x is equal to L times tan theta twice. So I got to do one for the red calculation. So let's do that quickly here. So I'm going to find the angle for the red. So N is 1 times the red wavelength. I'm going to change it into meters because D is in meters. And then take the sine inverse. So red's angle is 2.29 degrees. And then I'm going to just plug it into that formula, L times tan theta. So I'm going to go tan this angle. I'm doing it on my calculator right now. And times 1.2. So the x value is 0.048038 meters. Okay, I'm just going to store that in my calculator. Then we're going to do this all over again for violet. Let's find for violet. So sine theta n lambda over d. And we're using this for the violet light. So my lambda is going to be the 400 nanometers this time. Oh, just 1 second. All right, so found an angle here, 1.14599. Decimal, 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 a bunch of decimals there. Okay, plugging it back into this L tan theta formula. So 1.2 times the tan of this angle. I find a distance to the violet light to be 0.024048 meters. Okay, so this just confirms that the red light did interfere further down, and then the violet is a little bit less. So there is a difference between the two. So I just want to find that distance between the two. So what is the difference between them? So I'm going to subtract my two numbers. And get 0.024. How many sig digs? We need 3 sig digs. One more zero in there. Cool. Meters. That's about 2.40 centimeters. That's all. That's my answer. Cool. Hopefully that helped you out. Now, yeah, so this is the end of this chapter. So try out that test. You got the end of the week to finish off that test, and I'll see you in the next video. Bye.